Next, let's see what happens if we use degree 6 features to fit a logistic regression classifier on the same data set. So now our features go all the way up to x2 to the 6 and x1 to the 6. It's a lot more features, a lot more coefficients to be learned from data. Now if I take this data set and I feed it for logistic regression classifier, I get the following decision boundary. It fits the training data extremely well. If you look very carefully, it actually gets 0 training error, which would be a warning sign for you, by the way, as we mentioned. And if you look at the decision boundary, it's extremely complicated. Complex. Some people might say, here's a technical term for it, crazy decision boundary. So even though it has 0 training error, it has some weird artifacts to it. So for example, I'm highlighting here a region in the space where even though all around it's surrounded by a prediction it's positive, right in the middle of that circle, it thinks that the score should be less than 0. So for that region, we're saying that y hat should be -1. And it really doesn't make any sense to me, because right around it, every point is +1. Why should I expect the points in the middle there to be -1? The data doesn't support it at all. And in fact, if you look at the magnitude of the coefficients, they're starting to get large. While the natural parabola had coefficients of around 1 minus 0.5, now we're getting coefficients of the order of 42 or more, which are 10 to 40 times bigger than the ones that I had before. And that is early warning sign of overfitting, as we discussed in the regression class. Now let's take that one step further and fit a logistic regression model that uses polynomial features of degree 20. So this is going all the way up to x1 to the power of 20 and x2 to the power of 20. So really, really high order polynomials. If you look at the decision boundary that we learned, I mean, come on. I'll say that this, I can say it's truly crazy. Crazy. It's really, really complicated, gets all the data right, but it's highly unsmooth. And if you look at the learned weights, the coefficients are of the order 3,000, 4,000, minus 2,000. They're much, much bigger than that simple parabola that we learned. It gets all the training data right, but it's clearly overfitting, and it's clearly outputting very large estimated polynomials, very large estimated coefficients. And so we're going to watch very carefully to the magnitude of those coefficients when we try to avoid overfitting. So the notion of overfitting in classification is very similar to that of regression, except that the error now is measured in terms of classification error. And there might be some set of parameters that we learn here, w hat, which seem to do very well in the training data, maybe even as crazy boundaries, while there was some other parameter, w star, some other set of coefficients, w star, that would have done much better in terms of true error. And the question is, how do we go and push our learning process to be more like w star than it is to w hat? And we'll do that by pushing our parameters to be not as massive, not as huge, push them towards 0, as we did with regression, with regularization.